equation, which lays in the base of the theory of the turbomachinery, but it's most important equation, most important law, most important formula in the theory of the turbomachinery. That's why it's rather a big chapter. I hope we are completed today, but it's really very important. So I will share my screen. One second. Do you see the presentation?
Yes.
Perfect. 1 second. I may not see it. Okay. The last equations are called energy equation. Equation of angular momentum, or it's more famous like the Euler equation for the turbomachinery. It's really important equation, but we will discuss it in the future, of course. So, from the course of theoretical mechanics, you need to know equation and law of conservation of angular momentum. I hope, because, for example, in Russian course of theoretical mechanics, we are studying this law during studying course of theoretical mechanics. So, from this course, you know what resultant of all forces are acting on the body with the mass m, and which moving with the speed c, and spaced from the axis of rotation by distance r, creates the torque about x of rotation. And you could to calculate this. This momentum using this equation. So I hope you know this information from the course of theoretical mechanics. We will apply this information, this law, to the flow in the turbomachinery. So let's take the random turbomachinery. At this moment, it's not very important what kind of the turbomachinery it will be. It will be only a rotor wheel. And it could be any turbomachinery which you want. In my case, in the picture, you see the rotor wheel of centrifugal compressor. So, and we will make the same assumption like in the case of continuity equation. We will think what we know all flow parameters in the inlet of the rotor wheel at the section 1 and at of the rotor wheel at the section 2. So it means what we know every parameters which are important for us, like pressure, temperature, total temperature, velocity, flow angles, density, every parameters we know at inlet and outlet section. And let's split our flow to the huge number of the flow tubes, steam tubes. We will think what we are not supplying additional mass inside the tube, and we are not extract masses from the back side of the tube. It means what the flows comes only from inlet section and comes out only from outlet section. At first position, T0 equal to 0, the flow tube was in the position 1, 4. So at first time of the first period of the time, the tube was at this position. After very small period of the time, T0 plus dt, and dt will be leads to 0, the tube will be moved into the position 3, 2. So I forgot to say the small assumption. What the diameter of the steam tube so small, what we could to say, what the parameters in cross section 1, 2, 3, 4 could be uniform. It's the first moment, and the second moment, time period dt is too small. What we could to say, what the parameters between the section 1 and 3 and section 4 and 2 doesn't change. So the time which we are investigate very small, and flow have no enough time to change the parameters between the section 1 and 3 and 4 and 2. That's all. That's all. Our aim to apply this equation, this formula, to the flow which we are discuss above. So we need to apply equation of angular momentum to the case of the moving of the flow tube through the random turbomachinery. Of course, it looks a little bit complex. It really looks complex, and if you do not think everything what simplify your calculation, in reality it will be looks very complex, I think. But if we look carefully to this process, we could to simplify our equation. How what we could to find interesting inside this case? If you look carefully, we will find what the position, what the period 3, 4 is the same for the two cases. The part of the tube 3, 4 are the same for the two cases, for the time t0 and t0 plus dt, and this tube, I mean 3, 4, doesn't change during process which we are investigate. It's mean what the angular momentum of this element doesn't change. That's why we could avoid writing the equation for this part. We could extract it from our point of view, from our I find a lot of English words what I don't know. We could not take in account the process inside this tube because these tubes are not changed during the process, and angular momentum of this element doesn't change. So it's the first idea, and the second idea, what we could to say, what we have the constant element of the flow tubes, and at the time t0 the mass 1, 3 comes in, and we have this mass plus constant element. At time t0 plus dt we have constant element, but inlet element are disappear, it comes in, but from the outlet we are receive element 4, 2. So that's why this equation could be right only for this element and only for this element. But if we will look carefully to the first element, to inlet element, we could to say what at first time period it will be present. At the time period t0 plus dt, it's disappear. That's why momentum will be momentum of this element will be equal to the angular momentum of this mass at the first period of the time, because at the second period of the time it's disappear. And the same for the outlet mass. At first period of the time it's we have know it, and at the last period of the time it's appear. That's why momentum will be equal to angular momentum at the first period, but we have know this element. That's why at first period angular momentum equal to 0 minus angular momentum at the time period t0 plus dt, and of course it's equal to the angular momentum at the last period of the time. That's why finally we could to receive for all this tube such a equation of angular momentum. So you see what here we have relationship for angular momentum of output mass minus angular momentum of inlet mass. So if we are divide mass to the time, we are receive mass flow rate. That's why we could to a little bit simplify our equation. After that, we are transfer differential equation to the normal typical representation of physical equation, and after that we will multiply all parts of this equation to omega. This is angular velocity. It's measured in radian per second, and we will divide all parts to the mass flow rate. What we will receive? First moment, at the at the left part of equation, we will receive torque, momentum, multiplying to angular velocity. What it will give for us? What the physical value we will receive if we will multiply torque to the angular momentum? Guys, do you know what we receive at this relationship? No answer. So we receive power. I don't know which letter you are used to designate power, but we will use letter N to designate it. It will be power. And if we will divide power to mass flow rate, it will be power which produced or extract by 1 kilogram of the working fluid. By other words, it will be specific work. In future, we will discuss what is the specific work finally we are receiving. If we look to the right part, we could to simplify the right part of the equation, because we know what the omega, it's the angular momentum. If we are multiplying omega to the radius, we are receive circumferential velocity. That's why finally we will receive this equation, this formula, and this formula is the most useful shape of the equation of angular momentum for the turbomachinery, or by other words, it's the Euler equation for the turbomachinery. Okay, let's continue. What the source of the torque in the rotor of the turbomachinery. What's the main reason of appearance of the torque in the turbomachinery? Of course, I think you know, if you have X, it's at this picture X located normally to the screen surface, and you have some mass which are located at the distance r relative to the x of rotation. To create torque, you need to apply force to your mass. And that's why we could to say what the main source of the torque will be the force which impact to the blades of the turbomachinery, if we speak about the turbomachinery. That's why let's look to this problem from the other position. So, what kind of the forces are impact to the blades in common case? At this moment we will not take in account type of the turbomachinery. That's why we are look from the common position. So in reality we have two kind of forces which impact to the blades. First moment it will be gas forces. We are discussed it in previous lectures. So we have the blades, we are flow by working fluid around the blades, and finally we are receive pressure difference between the pressure side and suction side, and finally we are receive some gas force which impact to the blades. And this force, it's the gas forces which impact, which acting to the blades. It's the first kind of forces which impact, which acting to the blades in the turbomachinery. The next moment, you know what your blades, I mean blades inside the rotor wheel, blades on the rotor wheel are rotating. That's why we are moving with the relative velocity from one position, and the second moment, it's rotate. That's why inertia forces are impact to the flow at this impact to the flow, and we need to take in account. In inertia forces. At our case, it will be Coriolis force. How to calculate the gas force? Here, we will not spend a lot of time to receive this equation. I will give to you the results. So, but at few words, you could use this equation to calculate gas forces. As far as I remember, it's the Zhukovsky equation for the lift force of the wing shape, and you could to use it to calculate the force which you received during the flow working fluid around the wing shape profile. So here you could see how to calculate averaged velocity, and finally, if we know force, we could to calculate torque which are created by this force. You see what the equation could be simplified and have the shape very close to the shape of equation which we are received on previous slide. But only one difference, here you see what we are use relative velocity. W, it's relative velocity, and we are using relative velocity. In previous equation, we are using absolute velocity. And the same for the Coriolis force. I hope you remember the formula for calculating of Coriolis force, and I refresh the information what the Coriolis force are direct normally to the direction of the x and direction of the relative velocity. And based to the value of the Coriolis force, after some conversation, we could to calculate the value of momentum of the torque which are created by Coriolis force. Of course, assume torque, it's the sum of torque which are created by gas forces and torque which are created by Coriolis force. That's why to receive the common torque, the assumed torque which are acting to the blades, we need to assume the first equation and the last equation. So, finally we receive these two equations. First one will be for compressor. The second one will be for turbine. We do same actions like in previous slide. We are multiplying all equations for the to the omega. We are multiplying to omega and multiplying to 1 divided by mass flow rate. By other word, we are divided all parts of equation to the mass flow rate. And finally we receive such equation. So it's interesting moment. Okay, I will discuss it later. So if we will, this equation, these two equations are common equation. It could be applied for any compressor and any turbine. But you know what we have very often we use axial compressor and axial turbine, and the special feature of the such kind of the turbomachinery, what the direction of the flow approximately parallel to the direction of the x of rotation, and that's why for the axial turbomachinery we could to say what the inlet radius approximately equal to outlet radius. And for us, it's mean what the U1 approximately equal to U2. And that's why for the axial turbomachinery, the last equations will be simplified. So what we are do. So what we are do right now. So 1 second. We are receive the equation for the specific work of the turbomachinery, and we are receive it using two way, and we are receive a little bit different equation. The previous equation which we are discussed at this slide was received based to the equation of angular momentum, and you see what this equation, this formula contain projections of absolute velocity, and here we are receive the formula for the specific work based to the forces which impact to the blades, based to the forces which impact to the blades, and we receive a little bit different equation which are contain relative and circumferential velocity and circumferential velocity inside. That's why we could to make equal first kind of equation and last kind of equation, and we could to make it equal. So, and finally we will receive this equation, and we could to say this is Euler equation for the compressor and for the turbine. But of course, in reality, most useful part of this equation, this one. So usually when you are here about the Euler equation, usually it means this part of equation, but of course you could to remember what the left part of equation equal to the right part of equation, and sometimes during calculation more convenient to use right part of this equation. So, and the last idea here, specific, we will write Euler equation for the axial turbomachinery. And finally, we could to write it what specific work equal to circumferential velocity multiplying by delta WU, and it's equal to U multiplying by delta CU. And from this equation, you will see what for the case of axial turbomachinery, value of differences of circumferential projection of relative velocity and absolute velocity are the same in the case of axial turbomachinery. So we are receive Euler equation for the turbomachinery. It's really very important equation, very important formula for the turbomachinery. I think it's the main equation of the turbomachinery. In my opinion, approximately 80% of the turbomachinery theory based on this equation. It's really so. Like the stress calculating based on the Hook equation, the turbomachinery calculation based on the Euler equation. And in future you will see what in the case when you will need to analyze the working process of the turbomachinery, you need first action what you will need to do, you need to write Euler equation. And you need to analyze how the circumferential velocity are changed, how delta CU or delta WU are changed, and in many cases you will find the answer to your question, how the working process of the turbomachinery will change in your task. So that's why the main idea what I want to say to you at this slide, what this equation are most important equation and the keystone of the turbomachinery theory. So, do you have any questions, guys?
No.
Okay, let's continue. Of course, like in the case of the previous equations, for us, of course, it's important to understand how we are receive the equations and what kind of assumption we are using, what kind of simplification we are using. But of course, for us, is much interesting to apply these equations to the working process of the turbomachinery and find some conclusions, find some answers which will explain to us why the turbomachinery looks like we know. So, and let's apply this equation to the turbomachinery and let's try to find some interesting explanation which explain to us why the gas turbine engine looks like we know. First moment, before we will discuss the application, let's discuss what's mean LT. LT is the specific work which are located on the blades. What I want to say to you, for example, let's look let's make short brief about the working process of the compressor. How the compressor operates. You are supply some external work from outside to the blades. So you are take some energy from the turbine, for example, or from electrical generator, and you are transferred to the blades. And after that, from the blades, it will be blades. It will be turbine. And after the blades, using the blades, you are transfer this energy to the flow. And inside the flow, you are spent this energy for the compression. So, what's mean LT? LT, it's the energy which are supplying from the blades to the flow, or the blades which are extracting using the blades from the flow. So we could write the same scheme for the turbine. So this is scheme for the compressor. For the turbine, we have energy inside the flow. We are catching it using blades, and exact this energy could be calculated by Euler equation, and after that we are transfer it to consumer of the energy, for example, for compressor. These three works are not equal, because during each step we have some losses, and that's why these energies are not equal. So, but for you, it's most at this moment, the most important idea I want to say to you, what Euler equation allows to us to calculate specific work which we are extracting from the flow by blades, or which are supplying to the flow by blades. So, and let's try to look carefully to this equation and find some interesting conclusions. First moment, let's look to Euler equation. Do you see the density, temperature, fluid properties, moon phase, I don't know, electricity, something interesting at this equation? No, we have no density, we have no pressure, we have no temperature, we have no fluid properties. It's mean what the specific work which you are extracting using the blades, or supplying using the blades, not depend from the density, pressure, fluid properties, mass flow rate, and other parameters. It's really very interesting, because very often not only students, sometimes engineers thinks what the work which you extract from the blades from the flow will be depend from such parameters. In reality, if we look carefully to this equation, specific work will be depend only from two things. From the circumferential velocity and from the differences of circumferential projection of velocities. It's only two things. Of course, it maybe looks strange. Of course, why, for example, the work which we extract or supply using blades not depend for example, from the temperature or from the pressure ratio. But I could show to you example. I think it's the better to show based to the turbine. Let's imagine the working process inside the turbine. In the turbine, we have expansion process, and during expansion process, we are receive some energy. And value of energy which you are received during expansion process really depend from the fluid properties, from temperature, from pressure. But the energy which you are receive using blades depend from delta W and U. It means what if your turbine not rotate very fast, if your circumferential velocity very small, it means you are not take all energy which contain inside the flow. And if you are differences of circumferential projection will be very small, you couldn't extract a huge amount of energy from the flow. I think it's a good example. So it's the first conclusion. What the energy which you are receiving or supplying using blades depend only from circumferential projection, differences of circumferential projection of absolute or relative velocity and circumferential velocity. The second conclusion, a little bit strange. It's really a little bit strange. From the first position, it's not very clear how to use it. For example, you have the black box, and you know what inside this black box located some turbomachinery, but you doesn't know which kind of the turbomachinery are inside. But I don't know how, but you know the these values. You know U2 multiplying by C2U, and you know this value. And you could to imagine which value are higher. So, at this case, the situation looks very strange because I think in reality it's very hard to imagine what you don't know the type of the turbomachinery, but you measure these values. But let's imagine if U2 multiplying to C2U more than U1 multiplying by C1U, at this case, mechanical work is supplying to the working fluid. It means what you are, or what inside the black box will be compressor. If you have other relationship, if U1 C1U more than U2 multiplying to C2U, it means what you are extracting energy from the flow and you are receive the turbine. So, of course, this conclusion rather strange, but sometimes during calculation, during stage calculation, it will be maybe it's not correct word necessary, but I think it will be good idea to calculate relationship between this value. Sometimes, especially during student calculation, you could to receive what in your case in the compressor. You are calculate the compressor, and you are receive what U2 multiplying by C2U less than U1 multiplying by C1U. You could to receive such result during calculation. In 90% of the cases, it means what you are make mistake in your calculation, and it's a signal. It's the point after that you need to check your results. That's why I say about it. But At 10% of the cases, it could be dealt with the combination of initial data. Unfortunately, some combination of initial data could to provide not good results, and in reality you are calculating the compressor, but finally you are received the turbine. Sometimes it could be happen, but not very often. So, and of course, at this case, you will need to change the initial data. So, it's the second conclusion. Okay, let's go further. Of course, as usual, we want to increase specific work. Why? It's very simple. If you increase in specific work, we are speaking about the specific work of one stage, of course. We are not speaking about specific work of multi-stage compressor. Of course, we want to increase specific work of one stage. And how to increase it? If we will look to the Euler equation, we find few ways. Way number one, increasing circumferential velocity. How to increase it? It could be realized by two ways. To increase radius, or you could to increase rotation velocity, RPM, rotational per minute. Sorry. It's the first direction of increasing of specific work. And the second direction of increasing of specific work, increasing delta CU, increasing the difference between the circumferential projection of absolute or relative velocity. So let's discuss influence of the circumferential velocity to the working process of the turbomachinery stage. I have one very interesting example which could to illustrate influence of rotational speed or radius to the working process of the turbomachinery. For me it's much interesting by different reasons. One of them, what it's one reason, what it's the engine which we will discuss, engines which we will discuss are produced in the Kuznetsov company, which are located in Samara. It's our local example, but you will see what it's very interesting example. And other interesting moment, other ideas you will understand later. So here at this picture you will see a sketch of the engine NK37ST. This engine was received from the aircraft engine. So initially it was 3-shaft turbofan, this afterburner, which are using on the military aircraft. Initially it was engine NK32. But approximately 30 years ago, this engine was modified and converted to the ground application. So the bypass was closed, the low pressure compressor was modified, last stage of the low pressure turbine was removed, and of course the elements which are not used in the ground, in the power ground unit was removed. The mixer, the afterburner and nozzle was removed. And at the outlet part of the engine was mounted power turbine or free turbine. And using such ways was created two types of the engine. NK36ST. This engine are used for the drive of the gas pumping unit. And NK37ST, this engine are needed for driving of electrical generator. These two engines have the common gas generator which was created at the base of NK32. And the gas generator of both engines, I mean NK36 and NK37, are the same. And both engines are produce the same power, 25 megawatts, and they have the same cycle parameters. They have same mass flow rate, same pressure ratio in the cycle, and same total temperature before the turbine. So, and if we will look to the three turbine, if we will look to the power turbine, from the position of thermodynamic, for example, if you will calculate these two engines using Astra software, you will find what from the position of the thermodynamic, these two power turbine for these two engines are the same, because they have same mass flow rate, they have same temperature, they have same pressure ratio and same output power. From the position of the thermodynamic, it's the equal turbines. But what the difference? Difference in the rotational speed. The rotational speed of the power turbine are determined by the device which are consume the energy. For example, for the gas pumping unit, our typical rotational speed 5,600 rotational per minute. For the for the electrical generator, we are discussed on the previous lecture, the typical rotational speed 3,000 rotation per minute. So, and one additional moment, the sizes of the three turbine are the same, because the support, this element of these two engines are the same. It's have very similar construction in NK36ST and NK37ST. It's mean what the diameter and the blade height the same for two engines. So, and if we look to these engines, we will find what, because at the case of NK36ST rotational speed much higher, it's mean what with the same sizes circumferential velocity will be higher. And it's mean what the specific work of one stage will be higher. And that's why the same power, 25 megawatts, we are receive using only two stages. In the case of NK37ST, we have lower rotational speed. It's mean with the same sizes, it will be a lower stage specific work, and it's mean what the same power we are receiving using 4 stages. It's really very interesting example, because if we will look from the position of the thermodynamics, it's the same turbines. And the difference between these two turbines only at the one number. We have only one number difference, and we have very different construction. We have 2-stage turbine, and we have 4-stage turbine for the case NK37ST. And one additional moment at which I want to pay your attention. So, you see what the original construction of initial engine NK32, which lays at the base of gas generator, have rather small radius at the outlet of the turbine. And if you look to the radius of the free turbine, you will see what the free turbine have much more radius. And in reality, you will see what the engine looks like, looks a little bit strange. You have rather small diameter gas generator and big diameter power turbine. Why such decisions are used? Very, very simple. You see what the rotational speed of the rotors are not so much for NK36ST and NK37ST. That's why if you will keep the diameter like in initial NK32, you will receive small circumferential velocity and you will receive small stage specific work and you will receive a great number of the stages. So it means what you will receive 5, 6, maybe 7 stage free turbine. But of course you understand what so much stages strongly increase the cost of manufacturing of such turbine. And that's why if you are increasing radius of the turbine, you are increasing circumferential velocity u, and finally it's increasing specific work of the stage, and finally it's reduced number of stages. That's why for the engines which are convert from aircraft application to the ground application, it's really very typical. It's really very typical what the free turbine have high diameter to reduce. This is the main aim, to reduce number of stages of the free turbine. For example, if you will find ground application of Rolls-Royce RB211 engine, you will find approximately the same decision. It looks really the same. The small gas generator is the big diameter power turbine. So, okay, let's go further. Let's look carefully to this equation. We could to find what if we want to receive specific work using blades, the value which are located inside the brackets, I mean this one and this one, must be not equal to 0. Because if it will be equal to 0, the equation became equal to 0. So, it means what the circumferential projection of absolute and relative velocity must be changed. By other words, it means what for organizing energy exchange between the blades and the flow, you need to turn the flow. So, it's really a very important idea. It's really very important note. For providing energy exchange between the flow and the blades, for supplying or extracting of mechanical work from the flow, it's necessary to turn the flow in the blade channels. It's the first idea. The second idea, let's imagine you are calculate what for receiving the energy which you need to turn the flow, for example, to 20 degrees. How to explain to the flow what the flow must to turn on 20 degrees? You couldn't to say, hey, flow, turn to the 20 degrees. You need to use some devices which will turn the flow to the prescribed direction. And the blades, it's the special profiled elements which are turn the flow to the angle which we need. So, by other words, the main function of the blades to provide turning of the flow. And finally, it will lead to the energy exchange between the blades and the flow. So that's why I think, I hope I'm explained why we need to use the blades. Blades are direct the flow and they are leads to the turning of the flow. So, okay, let's discuss the working process in the compressor. If we look carefully to this equation, you will find what for receiving the positive specific work, we want to supply mechanical work to the flow, and that's why this work must be positive. For this reason, you need to provide what W1U must be more than W2U. If we look carefully to the velocity triangles in the inlet and at the outlet, and if we compare vectors of relative velocity, we could to find what for receiving such relationship between the circumferential projection of velocity, we need how to say, we need to provide what the beta 1 angle will be less than beta 2 angle. And of course, you see what the value of differences of the circumferential projection of relative velocity will be depend from the angles to which you are turn the flow. If you are increasing flow deflection angle delta beta, you will increase delta WU and you will finally increase the specific work. We will discuss it a little bit further. So finally, in the compressor, to provide energy exchange, you need to provide such shape of the blades, what the angle at the inlet will be less than angle at the outlet. And the same for the turbine. In the turbine, for extracting energy from the flow, you need to provide what W2U will be 2U will be more than W1U. And if we look to the velocity triangles in the inlet and at the outlet, you will receive what you could to receive such relationship if you will provide such combination of the angles. What the angle at the inlet of the turbine will be more than angle at the outlet of the blade row. So, okay. So, short brief about this slide. At this slide, we are discuss what if you want to provide energy exchange between the blades and the flow, you need to turn the flow. And the blades help to us to turn the flow. We direct the flow to the direction which we need. And we investigate the velocity triangle at the inlet and at the outlet of the blade row of the compressors and the turbine, and we will find what the relationship between the inlet and at the outlet angle of the compressor must be like here, and for the turbine must be like here. So, okay, let's come further. So, in the compressor, we need to provide what the beta 1 must be lower than beta 2. If we look the flow inside the flow channel, we will find what the cross-section area will be the relationship between the cross-section area at the inlet and at the outlet of the turbomachinery will be depend from the sinus beta 1 divided by sinus beta 2. And because beta 1 less than beta 2, we could to say what cross-section at the so what f1 divided by f2 must be less than 1, and it's mean what f1 less than f2, and it's mean what the shape of the channel between the blades will be diffuser. So by other words, if you are provide such a relationship between the inlet and the outlet angles in the turbomachinery, you are receive the diffuser channel. So a few words about the diffuser. As you know, at the diffuser, the cross-section area will be increased. And diffuser have one big problem, one big disadvantage. What the flow very often separate at the walls of the diffuser, and the probability of the separation depend from the diffuser angle. And if you are increasing this angle, you are increase the probability of separation, and finally you are increase losses. Of course, if you not want to receive the separation, you could to reduce this angle, but finally it will be leads to the increasing length of the diffuser. And increasing length of the diffuser increase the losses deal with the friction. That's why this increasing of this diffuser angle, from one hand you increasing probability of the separation, from other hand you are reducing friction losses. That's why we have two opposite factors which are impact to the value of such angle, and we have optimum value of this angle. As far as remember, the optimum value of this angle approximately 10-15 degrees. So, and of course, we remember what in the diffuser channel velocity will be reduced, and it's mean what W1 more than W2, and breaking the flow will lead to increasing the static pressure. And of course, we need to increase. Yes.
I have a question. What do you mean by separation of the flow?
Separation of the flow. Good question. it's very interesting question because I know what is it, but it's very hard to explain. Usually when the flow comes through the channel, the flow lines repeat approximately shape of the channel. But sometimes the flow could be separate. I don't know how to explain it. It's better to show maybe to show the picture. You are not understand it. So does it will be good idea to find the picture of the separation, guys?
Yes, I think I know what you mean, but I'm not sure. That's why I'm asking.
I could to find the picture. It's not big problem, but it spent a few minutes. Okay. Okay, let's try. Well. Second. I think if we speak about the separation, it's better to see it. So here, do you see it?
Yes.
So here picture from the water test rig. It was created by one student from Germany. You see the ink which are put inside the water. It's water surround the blades, and you see what this element. You see what at the first part of the flow around the leading edge, the path line repeat the shape of the blade, but at some moment it became to make rotation, oscillation, and some other elements. So the separations looks like at this picture. It's
Okay.
okay?
Yes.
Так, наверное, это надо убрать. Так. Так. So, do you see it?
Yes.
Perfect. So, let's discuss about the turbine. As you understand, in the turbine, we received the opposite picture. 1 second. In the turbine, if we will provide beta 1 more than beta 2, finally you will receive what the F1 cross-section area at the inlet must be more than cross-section at the outlet. It means what the channel in the turbine must have confuser shape. The confuser channel have no the problems with the separation, and it's provide the less value of the losses. It's the first moment, and of course in the confuser channel we have acceleration of the flow and pressure drop. So as we are discussed above, the value of delta WU will be depend from the value of delta beta, and of course, we are always want to increase specific work, and 1 second, and we are want to increase delta WU. And how to provide increase in delta WU? By increasing delta beta, by increasing of flow turning angle. Let's try to understand, does it will be good idea for compressor if we will increase delta beta angle? So at left picture you see compressor blade row, and you see equivalent diffuser which correspond to this blade row. Let's fix the angle beta 2, and so if we will speak about the delta beta angle, it's the angle this one. And if you increase it, you will increase flow turning angle, and it's finally could to leads to increase in specific work. But let's check, does it good idea? So let's fix value beta 2, and let's increase delta beta by reducing value of beta 1. So this is new shape of the channel, and gray line show the initial shape of the channel, and the shape of equivalent diffuser. Maybe it's not clearly seen, but I think it's seen. What the equivalent angle will be increased. So this angle will be more than this angle. As far as I remember, here 20 degrees and here approximately 60 degrees. So what I want to say to you, if you are increasing delta beta, you will increase equivalent diffuser angle, and it's finally increase the probability of the flow separation. It's the first moment. In any case, if you are increasing diffuser angle, you are increasing the probability of the separation. And the second moment, you are blend the channel, and that's why you have high probability of separation here. So if the diffusion factor will be very high, finally you are receive the separation from the suction side. That's why it is not good idea to increase flow deviation, flow turning angle in the turbine, because it's good to lead to the separations and it's good to lead to the huge losses. That's why in the compressors these angles are limited. The value of delta beta in the compressors must be less than 30 degree. It's very important. For example, during calculation, you will check value delta beta and try to not provide the delta beta more than 30 degrees. So in the compressor, we have confuser channel. Confuser channel are not have the problem with the separation. That's why you have no limitation to the flow turning angle. But of course, we have some angles which we couldn't realize on construction. For example, we couldn't realize angle 180 degree. It's mean what the flow comes inside the blades and comes out to the opposite direction. It's very hard to imagine such flow movement, the construction of such turbines. What I want to say, that's why we have some limitation to the value of the flow turning angle in the turbine, but this angle could be very high. For example, I know the turbines, it's high pressure turbines, which have angles approximately 130 degrees. So the main idea, what in the turbine, because we have no separation in the confuser channel, we could to provide much more flow turning angle, and it's finally increased delta W. Okay, few words about the flow deviation. If you have single profile like the wing profile, the profile will turn the flow, but if the profile are separate very soon, the direction of the flow will back. Finally, you are not receive delta beta. Finally, you are not turn the flow. If you make to provide the flow deviation, you need to create blade row. And if the space between the blades will be very small, blades will have high influence to the flow, and that's why flow deviation will be like you want, and flow do not return back to the first direction of the flow. But if you are realize such high solidity blade row, you are receive big friction losses because you have big friction area. That's why usually we are use blade row like here. But at this case, because we have pressure difference at the outlet, so for example, here we have low pressure, here we have high pressure, it's mean what then the flow leaves the trailing edge, it's have influence of the pressure difference, which turn the vector of W2 in the direction of reducing of beta 2. The flow deviation angle delta usually approximately from 0 to 3 degrees. It's not very big, but for example, it's have great influence to the working process of the compressor, because common angle, common flow turning angle, not so much. And that's why it's important to take in account flow deflection angle. So it's short brief about the flow deflection. Let's return back to the delta W. Because we have limitation of delta beta angle, this one, the value of delta W and value of delta Cu will be not so big in the compressor stage. And value of delta beta finally are limited the specific work which you could to realize in the compressor stage. In the turbine, the flow deflection angle, flow deviation, flow turning angle could be bigger, and that's why value of delta W will be higher. And what we are finally receive, if we are imagine what the circumferential velocity in the compressor approximately equal to the circumferential velocity in the turbine, in reality, if we will speak about the gas turbine engine, circumferential velocity do not have big difference. Maybe some 20, 30, 50 meter per second. So, and if we will make what the circumferential velocity in the compressor approximately equal to the circumferential velocity in the turbine, we will find what the turbine create a huge amount of the specific work. And we are supplying this specific work to the compressor. But because the value of the delta W not are limited in the compressor, we couldn't supply this energy at one stage without great losses. And that's why we need to use some numbers, few numbers of the stages to supply the specific work which was produced by turbine stage. That's why finally we receive what in typical gas generator of the gas turbine engine, one or two stage of the turbine drive a lot of stage of the compressor. Drive 6, 7, 10, 12 stages. So if the mass flow rate approximately the same, if circumferential velocity the same like in typical gas generator, number of compressor stages usually greater than the number of the turbine stages. So I think it's very interesting conclusion, and it's explained to us why the gas turbine engine looks like we know. I think it's very interesting conclusion. So, and it's really very typical. You could to find a lot of picture of compressor. You could to visit engine museum. You are in most case find the same picture. For example, this is, I don't remember what kind of engine, but this is Rolls-Royce Trent engine. I don't remember the number, but you see high pressure cascade. One stage of the high pressure turbine drive, as far as I remember, 7 stage of the compressor, high pressure compressor. Low pressure turbine, one stage, this one, drive 8 stages of intermediate pressure turbine. It's like at this example. But if we will look to the low pressure cascade of turbofan engine, we will find something strange. So you could to see one stage of the fan driven by 4 stages of the turbine. What's the difference? Why here one stage of the turbine drive a lot of stage of the compressor, but in the low pressure cascade this rule doesn't work? Why? Let's try to understand. If you are connect low pressure turbine and low pressure compressor, it's mean what the power of the compressor equal to the power of the turbine. Of course, here must be losses, but we will not take it in account. The what I want to say, the power of the compressor could be right like mass flow rate through the compressor multiplying to the specific work of the compressor. And the same for the turbine. Mass flow rate through the turbine multiplied by specific work through the turbine. And let's look to the working process of the low pressure cascade. Here, through the low pressure turbine, we have mass flow rate approximately equal to the mass flow rate through the core. And here through the fan, we have mass flow rate, assume mass flow rate through the engine. And we could to calculate it, G assume equal to G1 multiplying by M plus 1. What we finally have? Finally, we have what in the fan we have power which produced by huge mass flow rate, this value very big usually, and that's why specific work not so big. And that's why it's enough to one stage or maybe 2 stages to create, to supply the power which produced by low pressure turbine. In the turbine, we have opposite moment. The mass flow rate rather small, and that's why to creating this power, we need to increase specific work. And that's why we have a lot of stages at low pressure turbine. And of course, the rotational speed of low pressure turbine usually very small. It's determined by rotational speed of the fan. And that's why number of stages usually rather big. So, it's the last conclusion from this equation. So guys, do you have any questions?
No.
Perfect. So, I think it's enough for today. Today's lecture was very important because it's really very useful equation. And I remember to you what the turbomachinery theory base at Euler equation. And then you need to analyze the turbomachinery working process. First action what you are do, write Euler equation and try to understand what's changed. That's why it's really important. I think you understand it during next lectures. So I think that's all for today. If you have no questions, you could be free. Please continue your calculation. Please do not spend a lot of time. We need to move forward. If you have any questions, please write to me. I try to answer as soon as possible. So
Okay, thank you.
Thank you. That's all. Thank you for attention.
Goodbye. Thank you.
Thank you,
Goodbye,
sir.
guys.
Goodbye.
Bye. See you at the next week.